Hi, this is Amnon Geifman. In this video, I'm going to present our paper that is going to be published in ICCV25. I'm a third-year PhD student at KTH Royal Institute of Technology, and this paper is called On the Faithfulness Complexity Trade-off of Gradient-Based Explanations. In this video, we are going to go over this agenda together. First, we discuss what is an explainability and why it matters. Then we pose one research question that is important in explainability, and we're focusing on this work. And at the end, and next we propose a solution to the problem we posed. And finally, we go over future works and conclusions. So we may ask, what is explainability? To give you some context, I would start with some history. First, we had a problem, and we hired researchers, and they had to work for years on a problem, and they produced some research output after years that were understandable by humans, of course, because it's written in human language, and the mechanism that you reach to some conclusion was transparent. With the invention of machine learning, we had the same problems, but the way we reached to solutions was different. So we trained neural networks on gigantic amount of data. We could model output given the input. However, the mechanism of reaching to that decision by the model was not transparent. It was not known. So we hired more machine learning experts to work on the solution that we find with machine learning algorithms to make the decision-making process transparent. So we are interested in the mechanisms of a model reaching to a conclusion here. The output could be human understandable, but the mechanism could be arbitrarily complex because it is found by optimization and not by research and human understanding. So we might ask again, what is an explanation? The problem is that we, as humans, we don't know what, or it is very hard to define what an explanation is. But there are various different ways of explaining something, one of which is like perturbation, sensitivity analysis, or counterfactuals. There are many methods. In this work, we focus on attribution methods. In attribution methods, we are focusing on attributing contributions of features for reaching to such output. Among attribution methods, we focus on gradient-based attribution. So we use gradient explicitly. We focus on this method because it is well-defined mathematically and easier to formalize compared to other methods that are heavily engineered. One problem that we face when doing gradient-based attributions, or generally in explainability, is that if you use explanation methods out of the box, like simple methods, you get very complex and hard to understand explanations. Something like this. In gradient-based explainability, if you use just the gradient of the network with respect to its input, we get something like this. It's very hard to understand, it's noisy, and people started working on this, and empirically they realized that if they aggregate, if they perturb the input image and aggregate different gradients of the same image, they can create low-pass filters implicitly and make the quality better, or it's easier to understand, the complexity is lower. Later in the slides, we formalize, or we try to formalize what the complexity of explanation is, and we try to understand this. So to iterate our research questions in this work, the first thing that we observed is that if you use raw gradients, no low-pass filtering, the gradient-based attribution becomes very complex and noisy, hard to understand. The first question is why such thing happen? Why gradient-based attributions are very complex? And maybe another way to put this question is that what is the source of this complexity? Also, we are interested in knowing how this complexity can be reduced, and if we reduce this complexity, what are the trade-offs or what is happening under the hood? So let's go over our findings when we were studying these problems very fast. Then we go back and try to understand each point in more detail. Our first finding was that we could show formally and empirically that the source of explanation complexity is in the network and not in the explanation method used. We could also relate the spectral properties of attribution to the spectral properties of the network formally. So I'll make this clearer later in the video. We could also show that one of the major contributor factors to explanation complexity is ReLU activation. Now that we know that ReLU activation is actually a main contributor, we can change the activation function and see what happens in the complexity of attributions. Of course, we find a new set of solutions that allow us to navigate the complexity-faithfulness trade-off differently. Okay, now let's go over our findings in more detail. We want to understand what those mean. In order to understand these findings, we need two tools that I'm going to go over here. The first thing we need is called Fourier basis, in spatial domain. So it means the basis of Fourier, which are cosine and sine functions, they are expanding in an image. This helps us to quantify variations within an image in spatial dimensions. I have put some examples of such bases in this figure. From left to right, we go from low frequency information to high frequency information. The second tool we need is Fourier basis, but this time not along a spatial domain, but along pixel values. If you want to imagine what is happening, because this is a high-dimensional input, I cannot visualize the basis that we are using. But if you want to imagine what is going on, you can imagine one-dimensional function. So on x-axis here, we have value of each pixel. Let's say we have 1 pixel input, and this is the value of the pixel. And this is the function, and we can, because of Fourier decomposition, we can write this function as a sum over these sinusoidal waves. And what happens is that if you take the gradient of this function with respect to its input, that's what we do, right? In explainability, we take the gradient of the function with respect to its input, and the gradient is taken with respect to the value of pixel. We observe that gradient amplifies high-frequency information, so we get something that its high-frequency information is amplified, and the amplification is proportional to the frequency. Now, to understand how do we exactly use Fourier basis along spatial dimensions, I'm going to go over the example we saw before. If we use Fourier basis in an image, Fourier transform gives the same image in another domain, which is called Fourier domain. So if we see these images as functions over spatial dimensions, let's say I have a function, I give you x and y, and you give me the value of this point. This is a function, and I can take the Fourier transform of this. When the basis of Fourier is expanded along spatial dimensions, it gives me another function, which I have not visualized here. The other function that we get is called Fourier transform of this image. And the important thing to know about that function is that it decomposes our signal. This is a signal over space. It decomposes our signal into its frequency components. So we will see that this figure on the left, which has more noise in it, will have more high frequency components compared to this guy here. And this guy has more low frequency components because if you take the Fourier transform, you can compare the two. And if you imagine the previous slide we had about the Fourier basis, you could see that if you want to express this in terms of Fourier basis, you realize that you need to use this guy more, like this basis, more than this. But if you want to express this in Fourier domain, you can use lower frequency information more than high frequency information. So Fourier basis in spatial dimensions allow us to express the complexity in a quantitative manner. This allows to talk about complexity in mathematical sense. Or let's say this is how we chose to talk about complexity and quantify it. There might be other ways that we have not done here. Now to make it more clear for you, if you take this signal and take the Fourier transform, each signal is in 2 dimensions, and Fourier transform does not change the dimensionality. So we will have a 2-dimensional signal, and the x and y coordinates of the Fourier transform will be frequencies instead of space. And we use a trick here because analyzing a 2-dimensional signal is hard. We use a trick here, and we take the average over each radius, let's say, and each radius belongs in Fourier domain. It belongs to one frequency. So if you want to study more about Fourier transform, it's in Wikipedia, it's easy. But what we do is called radial profile. We take average in each frequency. If we take the average in each frequency, then we have only positive frequencies. And this is also called spectral density. If you take the radial profile and raise it to power 2, so you don't have negative numbers, you will have only positive frequencies and only positive values. And this is called spectral density by definition. And what we expect here is that this guy here is more complex. So in its radial profile, we expect more high frequencies, as I've visualized here in a cartoonish visualization. This is not actually a Fourier transform of this. This is just a cartoonish way of showing it. So I expect this guy to have a heavier tail, let's say, and this guy that has less high frequency information to have a faster decaying tail, right? So we can talk about the decay rate. This guy decays slower than this guy, and if it decays slower, it means it has more high frequency information. If it has more high frequency information, it means it's gonna look like this. It's gonna be complex. And this allows us to mathematically understand and study complexity of explanations or attributions in a quantitative manner. Also, we use Fourier braces along pixel values in a relatively similar way. Again, because it's a high dimensional function, I cannot visualize, but I'm using a one-dimensional function to visualize what's going on. Now let's assume this is one function and this is another function. Two functions are given to us, and we want to compare which one is more complex. Here, complexity is relative. It's not a absolute quantity, it's a relative quantity. We can say A is more complex than B. We can say that by comparing their high frequencies. So if we are given two functions, we can look at their Fourier transform and say, okay, function A is more complex than function B. So we will have a similar story here. We have a complex function and we have a simple function. We take Fourier transform of each and we take their spectral density. Here, because this function is one-dimensional, we don't need to use a radial profile. We can just raise it to power 2 and we get spectral density. Then, if you look at the spectral density, we expect the function with more high-frequency information to decay slower. So it will have more high-frequency information. And this allows us to say that, okay, this function is more complex compared to this function. Of course, we can talk about this decay rate in a quantitative manner. But now I'm just giving the intuition. The intuition is that if you have more high frequencies, it's going to be more complex. So now that we can quantitatively talk about complexity in space, in spatial domain of attribution, and quantitatively talk about complexity of function, a natural question is that whether these two complexities are related. Can we relate them? If we can, how? Note that usually, intuitively, we tend to take this for granted. Like we will say that, well, we have a complex function and it leads to a complex explanation. This means that we have taken this relationship. We have taken this relationship for granted. We assumed that, yes, complexity in function space leads to complexity in explanation. But is that really the case? Now, relating these two, like complexity in function space and spatial domain, they are not that easy. The reason is that, although we do have access to the spatial Fourier transform of the attribution, we don't have access to the Fourier transform of a network. And that is almost impossible to take. So we don't have the Fourier transform of one to see if these two are connected or related. What can we do? Note that when we wanted to talk about complexity, we didn't need to look at all the spectral density of the function. We just needed to look at its tail or its high frequency behavior. Does it have a heavy tail or not? Something like that, to talk about if it is more complex than. So we would say that A is more complex than B because it has a heavier tail. That means we just need to look at the tail of the function. So we don't need the Fourier transform or full Fourier transform of a function. We just need to know some of its properties. Now the question is easier. We don't need the Fourier transform of the function. We just need a property of a Fourier transform. But the question is, okay, we don't have the Fourier transform, but can we talk about this property? Turns out we can. We need another tool here to talk about general function behavior, which is called neural tangent kernels. I will put some references about neural tangent kernels and how we study them in this work in the description of the video. The thing that intuitively we need to know here is that these functions that we create with neural networks can be seen as functions that somehow measure similarities between samples in the input space and give similar labels to samples that are similar. But the question is, what does that similarity measure look like? Is it like a Gaussian similarity or is it like a Laplace similarity? And it turns out that they have studied neural tangent kernels and they have shown that, or people have shown that the functions that we get from neural networks measure similarities with Laplace kernel, or it's very similar to Laplace kernel. And one distinguishing factor of Laplace kernel is that in Fourier domain it has a very heavy tail. If you want to imagine or intuitively think about it, think of it as a spatial domain. Like this is the different pixels that you can put next to each other, and this is the value of pixels. So if I want to visualize one image, I can show it as one line. This visualization needs some time to be understood. If you need, please stop the video and think about it. This is the different pixels, and this is the pixel values. So if I go high, this pixel is brighter, and if I go down, this pixel becomes dimmer and dimmer. Like here is black, and here's white. This is one pixel. And because images are spatially correlated, like if you look at one pixel, you can tell the value of neighboring pixels. We can think of it as a smooth line here. This is also simplifying assumption, right? We are assuming that this can be shown as a continuous function. But this is one example, like a training example, and we take this similarity with respect to this training example with Laplace-like kernels. And that means when we meet the training example, we have a very sharp change. And we may have one other sample that may cross these sharp points. Now, an interesting thing is that in NTK studies about NTK, people usually assume ReLU. There are other works that don't assume ReLU, but mostly works are focused on ReLU. And a natural question is that, okay, if we replace ReLU with a function that is smooth at this breaking point, or smoothed version of ReLU, and we make this a hyperparameter. We can make this as sharp as we want, and we can make it as smooth as we want. What happens to the resulting NTK? Or what does the similarity measure look like? Does it look like Laplace still or not? One thing we showed in this work is that if you do this replacement, it is like a few lines of math to show that the kernel becomes smoother. Now the kernel becomes smoother. It's not as smooth as Gaussian, but just to assume, just to intuitively visualize, we compare a Gaussian kernel, a smooth kernel, and a sharp kernel that is resulting of ReLU. So think of it like that. This kernel is a result of using ReLU in your architecture, and these smoothed kernels are a result of using this soft or smooth activation function. Now it turns out that with these we can talk not about the Fourier transform of the function, but we can think of some or guess some properties of the resulting function. If we use ReLU, we will have a function with sharp transitions. If we replace those if we replace the activation of ReLU with some smooth activation, we can smoothen the sharp points of our function. So we will have a function with less sharp transitions. That means when we take the gradient along this example that we want to explain, instead of sharp transitions in gradient value, we will have smoother transitions. And that means if we think of the Fourier transform of our gradient of the function, here we don't want the of the function, we want the gradient because we want to talk about its Fourier transform. We want to talk about we want to relate it to explainability, and explainability is on the gradient, it's not on the function. But the story is relatively complete now. We can talk about the tail. We don't need to talk about the Fourier transform. We can say, okay, this function that has less sharp transitions will have a faster decay, and this function that has a lot of sharp transitions is more likely to have a heavy tail. Okay, now we did this experiment in practice. It's more than just mathematical intuition. We actually did this. We have a function with ReLU activations, and we take its gradient, and it looks like this. No surprise, we expected this. The function attribution is usually complex like this. And instead of ReLU, we replaced ReLU activations with soft plus functions, which are approximations of ReLU, and it could be as precise as we want, depending on the hyperparameter of soft plus. We used, let's say, a smoothed version of ReLU, and we trained the function, and we realized that the complexity, which we want to quantify later with spatial Fourier transform, the complexity reduces. So we go from high complexity to low complexity. To make this quantitative, we take the spatial Fourier transform of this, and we change the value of soft plus, the hyperparameter of soft plus. The bigger the value of hyperparameter, the closer soft plus becomes to ReLU. So if this beta goes to infinity, we recover ReLU. If beta goes to smaller values, it becomes a smoother and smoother function. And we take the Fourier transform in each beta value, and we visualize this. This is actually a computation. It's not a cartoonish visualization like before. And we realize that the tail becomes heavier and heavier as this beta goes higher and higher. And at some point, when the beta is very high, we recover ReLU, which means we now know that the function complexity is indeed related to attribution complexity. We quantified this relationship. Not only we quantified this relationship, but also we formalized the relationship. We went from just an intuition that complex functions lead to complex attributions. We made this relationship formal and quantitatively measurable. Now, one problem of reducing the complexity of complex attributions is that people usually take a Gaussian blur on these or perturb the input and average them. Usually methods do aggregation over these, as I explained before. It has been shown by a previous work that these perturbations create a smoother surrogate for the complex function that we have. And the smoother surrogate is not exactly the original function that we started with, right? So the attribution of the smooth surrogate is smoother. Yes, it's easier to understand. Yes, but there is a problem. The attribution is not the attribution of original function. So now we have one problem that arises from post hoc reducing the complexity, or reducing the complexity in a post hoc manner. So we can now measure unfaithfulness and complexity. Complexity we talked before. And we can see that if we use ReLU, this line belongs to ReLU. If we take a vanilla grad, like the simplest thing you can do, just gradient, like this guy, and do some post hoc reduction of complexity, you reduce the complexity like this. You go to the left, so you're reducing the complexity, but at the same time you are introducing unfaithfulness. Now it means it's not talking about the original network, it is talking about a soft or a smooth surrogate that is implicitly created by perturbations. Instead, if we change the activations from ReLU, and I must emphasize that changing activation is only one way of controlling the complexity of the resulting function. We chose activation because we had the theoretical tools in our hand, like NTK. But in future, people may take batch norm, or I don't know, residual connections. A lot of things contribute to complexity. So people can take those and try to formalize or empirically study each component in the network and figure out how they change the function complexity. And in turn, they may lead to a simpler or more complex attribution. If we do this not post hoc, this is anti hoc, because we are doing this before training, because we are deciding on activation before training, right? And if we train this, if we do vanilla grad, we are very low on complexity, as you can see. At the same time, we are faithful because we are not creating a smooth surrogate for this function to be smooth, right? So it is at the same time both faithful and less complex. This means this is a Pareto frontier for this optimization problem, to be both faithful and less complex. This allows us to navigate this complexity faithfulness trade-off in a different way. Okay, let's talk about conclusion and future work. I want to iterate our findings very fast. So we formally and empirically showed that the source of complexity is in the network, is in the complexity of the network that leads to attribution complexity. Some people may believe that it is the result of my explanation method, so I will change the explanation method. The post hoc people who do post hoc explanation usually, or it is logical to believe that way, that okay, the source of complexity is in my explanation method, so I need to edit or design different explanation methods to get a less complex explanation or attribution. Instead, we showed that no, it is not. The source of complexity is not in your explanation method, but rather it is in the complexity of the network you are trying to attribute or explain. As we have shown, we related the tail of the spatial Fourier transform of attribution to the tail of Fourier transform of network. So we related spectral properties of attribution and the network. We also showed, formally and empirically, that one of the contributing factors is ReLU activation, and we verified our theoretical and intuitive view with changing activation, with a smoother activation, and showing that, look, it is resulting in a smoother and simpler attribution because we are creating a simpler function. And finally, we showed that, I must emphasize again, that changing activation is only one way to reduce the complexity of a function. I believe there are many more ways, and I hope people start making this explicit, that okay, this relationship is known now, my target is reducing the complexity or tail of the function. So we showed that changing activation is one way to make function less complex and navigate the complexity faithfulness trade-off, or a smarter way to navigate this trade-off. One thing that I see as a low-hanging fruit is that a comprehensive empirical study that compares effect of these architectural components. Okay, this guy studied activation, I would do batch norm, I would do residual connections, I would do, I don't know, positional encoding, things like that in VRTs. So this is a low-hanging fruit, a comprehensive empirical study of these components, the effect of these components on attribution complexity. Another way is to do, then when we do this empirical study, the path is open for a unifying framework that can justify all observations in one framework, theoretically. Also, When we can quantify this complexity, we now can add this complexity as part of our objective in a neural architecture search. Thank you for your attention. This was our presentation. Please feel free to ask questions in the comments or just email me.